Are acids and bases? How can you know them when you see them in the laboratory? A neutral solution contains an equal number of hydrogen ions and hydroxide ions. Pure water is a neutral solution. Neutral solutions have a pH of 7.0 on the pH scale. Acids are substances that increase hydrogen ion concentration in a solution. Acids increase the acidity and lower the pH of the solution. They are characterized by having a sour taste, such as in lemon juice or vinegar. An acid will react with and neutralize a base. Acids usually begin with an H, such as HCl, hydrochloric acid, or H2SO4, sulfuric acid. Bases are substances that contain the hydroxide ion, OH-, such as NaOH, sodium hydroxide. Bases decrease hydrogen ion concentration in a solution, increasing the alkalinity and raising the pH. They are characterized by having a bitter taste and feeling slippery like soap. A base will react with and neutralize an acid. Litmus paper is commonly used to indicate the pH of acids or bases. Acids turn blue litmus paper red, and bases turn red litmus paper blue. The pH of acids or bases can also be revealed using various indicators. Bromophenol blue is a pH indicator that can test pH levels between 5.5 and 8.0. Other indicators can be used to test for higher or lower pH ranges. Formulas for acids usually begin with an H because acids have hydrogen as the cation and some other substance as the anion. An acid consisting of anions that do not contain oxygen is called a non-oxy acid, and the prefix hydro begins its name. The prefix is followed by the root word of the anion, and the suffix changes from "ide" to "ic." Names of acids end with the word acid. Examples include hydrochloric acid and hydrocyanic acid. If you have the formula HBr, how would you name the acid? You know that this is a non-oxy acid because the anion does not contain oxygen. Begin with the prefix hydro. Add the root of the anion with the suffix changed to "ic, and then add the word acid to the end. HBr is hydrobromic acid. Other acids are called oxyacids because they contain oxyanions, which have ate and ite endings in their names. Oxyacids do not contain the prefix hydro. Instead, the name of the acid begins with the root part of the anion's name, and the ending changes. If the anion ends with ate, the ending becomes ic, like sulfuric acid. If the anion ends with ite, the ending becomes us, like sulfurous acid. A good way to remember how to change the ending of the anion is to use the mnemonic device, ic, I ate a poisonous bite. The ending ic goes with ate, and the ending us goes with ite. So for HNO3, which is composed of hydrogen and the oxyanion nitrate, the name is nitric acid. For HNO2, which is composed of hydrogen and nitrite, the name is nitrous acid. Bases are named differently from acids and don't have the word base in the name. Bases have a metal as a cation and usually have hydroxide as the anion. Bases are named according to the standard rules for naming ionic compounds. The name of the cation followed by the name of the anion. In order to write the chemical formulas for acids and bases correctly, you have to know the charges of the cations and anions that comprise them. The periodic table can help you remember charges for cations and anions formed from the representative elements. You also may be provided with a reference sheet that has a table listing charges for common polyatomic ions. To write correctly the number of atoms in the formula for an acid or base, you have to make the charges of the cations and anions equivalent. For example, sulfuric acid is composed of the cation hydrogen, which is a group 1 element that forms ions with a 1+ charge. Sulfuric acid also contains the polyatomic ion sulfate, which is shown on the reference chart as having a 2- charge. For the charges to be equivalent, sulfuric acid must be composed of 2 hydrogen ions and 1 sulfate ion. Sulfate does not appear in parentheses because there is only 1 in the formula. For aluminum hydroxide, the cation is aluminum having a 3+ charge, and the anion is hydroxide, a polyatomic ion having a 1- charge. In order for the charges to be equivalent, 3 hydroxides must accompany 1 aluminum. Notice that hydroxide is in parentheses in the formula. When there is more than 1 polyatomic ion in the formula, the whole ion must be shown in parentheses with a subscript to indicate how many are in the molecule.
In this compound, how are the bonds between the copper atom and the hydroxide ions different from the bonds between each oxygen and hydrogen atom? Why does there appear to be a space between the copper and the hydroxides? Why do the hydrogen atoms appear to be pushed into the oxygen atoms? Some compounds contain both covalent and ionic bonds. These compounds contain polyatomic ions. In the copper-2 hydroxide pictured here, covalent bonds exist between the oxygen and hydrogen atoms that form polyatomic hydroxide ions. Ionic bonds exist between the copper-2 ion and each hydroxide ion. Polyatomic ions are made up of covalently bonded atoms that act as a unit and have a charge. Because of their charge, polyatomic ions can form ionic compounds with other ions. This table gives the names, chemical formulas, and charges of some common polyatomic ions. Notice how ammonium is the only positive polyatomic ion among those listed. Most polyatomic ions have a negative charge. Look at the names of the polyatomic ions in the table. The bi in bicarbonate doesn't mean 2. Bi indicates that hydrogen is found in the ion. Sometimes bicarbonate is called hydrogen carbonate. Di is the prefix that means 2, like in dichromate. Per means 1 more oxygen, so perchlorate has 1 more oxygen than chlorate. Hypochlorate is a common polyatomic ion found in bleach and other products that can be used as disinfectants. Compounds containing hydroxide are found in drain and oven cleaners. Hydroxide-containing products are also used in the production of soaps and paper. Remember that bases contain greater concentrations of hydroxide ions. Cyanide is a polyatomic ion that has many uses in pest control. Cyanide is very poisonous to humans. Chemical compounds containing chromate or dichromate are used in the process of chrome plating. The names of some polyatomic ions sound similar but have different endings. The endings follow a pattern involving the number of oxygen atoms that make up the ion. An ion that ends in -ate has 1 more oxygen atom than a similar ion that ends in -ite. Notice that, although there is a pattern, the endings do not specifically indicate the number of oxygen atoms in the ion. The rules for naming compounds containing polyatomic ions are very similar to the rules for naming ionic compounds. The cation is still named first, and the anion is still named second. Unlike covalent compounds, prefixes are never added to indicate the number of atoms or groups of atoms that make up a compound containing polyatomic ions. When the polyatomic cation ammonium bonds with the polyatomic anion hydrogen carbonate, commonly called bicarbonate, they form ammonium bicarbonate. When ammonium bonds with an anion formed from a fluorine atom, the name of the compound is ammonium fluoride. When a sodium atom loses an electron to become a sodium ion and forms a bond with the polyatomic hydroxide ion, the name of the compound is sodium hydroxide. When a copper-2 ion, Cu2+, forms a compound with polyatomic hydroxide ions, the name of the compound is copper-2 hydroxide. Remember that Roman numerals are required for elements, such as copper, that can form ions with different charges. PbSO4 is an ionic compound sometimes found in the electrodes of car batteries. What is the name for this compound? Look at the formula. PbSO4 is made up of two ions, a positively charged lead ion and a negatively charged sulfate ion. Lead is in group 14, so it can form ions with different positive charges. Sulfate has a 2- charge. Remember that charges are crisscrossed to get the subscripts in the formula. Lead has no subscript in the chemical formula, which indicates that the positive and negative charges have canceled. Therefore, lead has a 2+ charge, and the name of the compound is lead-2 sulfate.
Water, H2O, is a relatively small molecule, yet it has a fairly high boiling point at 100 degrees Celsius. A similar but larger molecule, H2S, has a boiling point of -60 degrees Celsius. What accounts for the relatively high boiling point of water? Water has a high polarity, which gives it the important properties of a relatively high boiling point and the ability to dissolve many substances. Polar molecules have regions of both positive and negative charge that result from an unequal sharing of electrons among the bonded atoms. The types of bonds that form a molecule affect its structure and geometry. Valence electrons are the most important electrons for determining the structure of a molecule. In the main group elements, outer shell valence electrons are the only electrons used in forming chemical bonds. In some transition elements, inner level d electrons are considered valence electrons because they are involved in bonding. An electron dot structure represents an atom's valence electrons. These diagrams were devised by chemist Gilbert Lewis, who first used them with his college chemistry students in the early 1900s. Remember that the number of valence electrons for main group elements corresponds to the group number. Lewis used diagrams that we call Lewis structures to represent the arrangement of electrons in a molecule. Lewis structures show how valence electrons are shared among the atoms in a molecule. A single line or a pair of vertical dots represents a single covalent bond. Because they represent shared electrons, most Lewis structures satisfy the octet rule. In a Lewis structure, a nonmetal atom will be surrounded by 8 electrons. An exception is a hydrogen atom, which will be surrounded by only 2 electrons. Each dash or pair of dots represents 2 electrons. In both of these Lewis structures for water, the oxygen atom is surrounded by 8 electrons, and the hydrogen atoms each have 2 electrons. To determine the Lewis structure for a molecule, first count up the sum of all valence electrons for the atoms in the molecule. For example, Phosphorus trichloride, PCl3, has 1 phosphorus atom and 3 chlorine atoms. You would count 5 valence electrons for the 1 p atom, for a total of 5, and 7 valence electrons for each of the 3 chlorine atoms, for a total of 21. The sum of all valence electrons for PCl3 is 26 valence electrons, so the final drawing must have 26 electrons represented. After the number of valence electrons has been determined, the next step is to determine the arrangement of the atoms in the molecule's Lewis structure. Many simple molecules that are made up of more than 2 atoms consist of a central atom surrounded by other atoms. As a rule, if a carbon atom is present, it is drawn as the central atom. Otherwise, choose the least electronegative atom for the center. Electronegativity is the ability of an atom to attract electrons. Remember that fluorine, F, has the highest electronegativity of all atoms, and that electronegativity increases as the elements are closer to fluorine. Phosphorus, P, is drawn as the central atom because it is less electronegative than chlorine, which is closer to fluorine. Next, use single bonds to connect the other atoms to the central atom. A single bond is represented by either 2 dots or a single line. For every single bond that connects the central atom to a terminal atom, subtract 2 electrons from the calculated total number of valence electrons. With the remaining valence electrons, add lone pairs of electrons around all terminal atoms that aren't hydrogen. To satisfy the octet rule, each terminal atom will have 8 electrons around it. Subtract the number of electrons added to the terminal atoms from the total. If any electrons remain, add the rest of the valence electrons to the central atom. Now, check the structure to be certain that you have used the correct number of electrons and satisfied the octet rule. PCl3 has 26 total valence electrons. The Lewis structure has 3 single bonds with 2 electrons each and 10 lone pairs, for a total of 26 valence electrons, which matches the calculation. Each nonmetal is surrounded by 8 electrons, which satisfies the octet rule. Often a Lewis structure, such as NH3, contains hydrogen. Remember that hydrogen is stable with only 2 valence electrons, so it is an exception to the octet rule. Each hydrogen will have only 2 electrons. As you advance in chemistry, you may see atypical Lewis structures that demonstrate other exceptions to the octet rule. If your drawing has more electrons than you determined it should have, then the molecule most likely has a double or triple bond. The single line of a single bond represents 2 shared electrons. A double bond is made up of 4 shared electrons and is represented by 2 lines. A triple bond is made up of 6 shared electrons and is represented by 3 lines. For example, in drawing the Lewis structure for ethylene, C2H4, you would determine that it has 12 valence electrons, 4 for each carbon and 1 for each hydrogen. After creating the Lewis structure with 5 single bonds, you would calculate that you have 2 extra electrons that need to be added to the structure. Each hydrogen can only have 2 electrons, so the extra valence electrons must be added to one of the central carbon atoms. Each hydrogen atom will have 2 electrons, but each carbon atom should have 8 electrons. One of the carbon atoms violates the octet rule by only having 6 electrons. The 2 valence electrons on the other carbon atom are for a double bond between the carbons. The double bond shows that the carbons share 4 electrons, which gives them each 8. Now the structure has the correct number of valence electrons and satisfies the octet rule for carbon. To recap the steps for creating a Lewis structure, we'll look at a molecule of hydrogen cyanide, HCN. First, use group numbers on the periodic table to determine total valence electrons. Then determine the arrangement of the atoms. Choose carbon as the center if it is present, and, if it is not, choose the least electronegative atom, the one farthest from fluorine. In this case, carbon is placed in the center. Next, use single bonds to connect the atoms. Subtract 2 electrons from the total electrons for each single bond used. Then place the remaining lone pairs of electrons around the terminal atoms to satisfy the octet rule. Remember that hydrogen is an exception and needs only 2 electrons, so the 6 remaining electrons are only placed on the nitrogen atom. Check to see that your structure has the correct number of electrons and satisfies the octet rule. The HCN structure has the correct number of electrons, but doesn't satisfy the octet rule for carbon, because it only gives carbon 4 valence electrons. This indicates the need for double or triple bonds. Some of the lone pairs of electrons placed around the nitrogen are needed for the carbon atom. Carbon and nitrogen would share 2 electrons with a single bond, 4 with a double bond, and 6 with a triple bond. Carbon shares 2 electrons with hydrogen, so it has to have a triple bond with nitrogen in order to satisfy the octet rule. What kinds of properties do you associate with metals? What do you think gives metals those qualities? A majority of the elements found on the periodic table are metals. With the exception of hydrogen, all elements to the left of the staircase line are metals. Most metals are shiny and can be easily shaped. The metallic bonding of atoms is what gives metals these properties. Metallic bonds share similar properties with ionic bonds. Like ionic bonds, metallic bonds are based on the attraction between positive and negative particles. The atoms in a metal form a lattice that is very similar to the lattice structure formed between a metal and nonmetal in an ionic compound. Metallic bonds are found only between metal atoms. Metal atoms, like these aluminum atoms, don't donate electrons to one another, and they don't share electrons exclusively with each other. Instead, valence electrons overlap among the metal atoms. The valence electrons on most metals are only weakly attracted to the nucleus. When many metal atoms collect together, these valence electrons leave the individual atoms and move freely from atom to atom. These free-moving mobile electrons are called delocalized electrons. They no longer permanently belong to any one atom. This arrangement of metal atoms is often called the electron C model. When a neutral sodium atom bonds with other sodium atoms, the valence electron moves from the outer shell to the sea of electrons and causes the sodium to become a positively charged cation. These sodium cations are then attracted to the sea of delocalized electrons around them. The attraction causes metallic bonds to form among the metal atoms. It also causes the atoms to arrange themselves in a lattice structure. Note that the metallic bonds that form among atoms of the same metal, such as aluminum atoms, are different from the covalent bond that forms between 2 atoms of the same nonmetal, such as 2 chlorine atoms forming a diatomic molecule. In metallic bonds, the electrons move freely from atom to atom. In covalent bonds, electron pairs are shared by 2 specific atoms. The electron C model gets its name from the fact that valence electrons move easily within metallic bonds, just as water in the sea flows easily. The high mobility of electrons causes metals to be excellent conductors of heat and electricity. Other properties of metals, such as malleability, ductility, hardness, and strength, are also a result of the delocalized nature of the atoms in a metallic bond. Metals are generally malleable, which means that they can be formed into thin sheets, and ductile, which means that they can be drawn into thin wires. The delocalized nature of metallic bonds makes metals malleable and ductile. When a force is applied to a metal, one plane of metal cations can slide past another layer without breaking any bonds. Although the cations are mobile, they have a strong attraction to the electrons around them. This makes metals durable so they can be shaped without breaking. Hardness measures either a material's ability to resist being scratched by another material or its ability to scratch another material. Strength measures a material's ability to resist an applied force. The hardness and strength of a metal depend on the number of delocalized electrons. Metals with more valence electrons will contribute more delocalized electrons to the sea of electrons, and they will have greater hardness and strength. Transition metals, which have greater numbers of valence electrons, are considered strong. The alkaline earth metals are softer than the transition metals, and the alkali metals are the softest metals. The nature of metallic bonds also explains the extremely high boiling points of metals. Because the cations and electrons in a metal are mobile, the melting points of metals are only moderately high, and the boiling points are much higher. The melting point is the temperature at which a substance changes phase from a solid to a liquid. With the exception of mercury, which is liquid at room temperature, metals generally have moderately high melting points. In a metallic bond, the cations and electrons are mobile, so it does not take an extreme amount of energy to cause the ions to move apart and enter the liquid stage. The boiling point is the temperature at which a substance changes phase from a liquid to a vapor. Metals change from a liquid to a vapor when metallic bonds are broken. The boiling points of metals tend to be very high, because metals require a lot of energy to overcome the strong attraction between cations and the sea of electrons in order to break metallic bonds.
What information can you infer from the Lewis structure of this ammonia molecule? It is important to be able to predict the shape of a molecule. Many of the physical and chemical properties of a molecule are dependent on the molecule's shape. For instance, molecular shape influences whether two molecules can get close enough to react. Molecular shape is important in the body. Organisms contain proteins called enzymes that increase the rate of chemical reactions in the body. Each enzyme has a shape that allows it to bind to a specific substance and produce other products. For example, the shape of the enzyme sucrase allows it to bind to the sucrose molecule and break the molecule down into glucose and fructose. While a Lewis structure gives a general two-dimensional representation of the kind of bonds that are formed between ions, it does not indicate the actual geometry of the molecule. However, a Lewis structure can be used to devise a model that does indicate the shape and geometry of a molecule. This model is called the valence shell electron pair repulsion model, or VSEPR model. When creating this type of ball and stick model to represent a molecule, remember that balls indicate both the central atom and the terminal atoms. Sticks indicate bonds between the atoms. Large lobes are often used to represent lone electron pairs on the central atom. VSEPR models are based on theories about how the orbitals of valence electrons overlap. Different densities of overlapping orbitals will change the shape of a molecule, moving the atoms farther apart or closer together. The VSEPR bonding theory states that shared and lone electron pairs are geometrically arranged so that the electron pairs are as far apart as possible. The VSEPR model arranges both lone pairs of electrons and shared electrons around the central atom. The angle between two terminal atoms is called the bond angle. Electron pairs between atoms repel each other so that the bond angle between the atoms is maximized. A lone pair of electrons tends to occupy more space around the central atom. Because a lone pair takes up more space, it tends to push shared electron pairs closer together. Two lone pairs take up even more space, so the bond angle decreases as terminal atoms are pushed closer together. Notice how the bond angle between 4 shared electron pairs in the model on the right is greater than the bond angle between 3 shared electron pairs and 1 lone pair in the model on the left. The lone pair on the central atom pushes the terminal atoms closer together and decreases the angle. The various shapes that molecules can form are often categorized based on the number of electron-dense regions that surround the central atom of a molecule. For example, both of these molecule shapes are categorized as having 4 electron-dense regions. The one on the right has 4 shared electron pairs, while the one on the left has 3 shared electron pairs and 1 lone pair. The first category of molecular shapes is molecules with 2 electron-dense regions around the central atom. The Lewis structure for carbon dioxide shows 2 regions where the central carbon atom is sharing electrons with oxygen atoms. According to the VSEPR theory, the 2 regions will repel each other so that they are as far apart as possible, which in this case is 180 degrees. The shape of the carbon dioxide molecule is said to be linear. The next category of molecular shapes is molecules with 3 electron-dense regions around a central atom. The Lewis structure for boron trichloride, BCl3, shows 3 regions surrounding a boron atom. These 3 regions repel each other, so the VSEPR theory predicts that the chlorine atoms have bond angles of 120 degrees to maximize the distance between the electron pairs. The name of this molecular shape is trigonal planar. Another category of molecular shapes is molecules with 4 electron-dense regions around a central atom. 4 of these regions surround a central carbon atom in a molecule of methane, CH4. The VSEPR theory predicts that the 4 regions are oriented so that the bond angles between the atoms are each 109.5 degrees. The shape of this arrangement is called tetrahedral. Ammonia, NH3, also has 4 electron-dense regions, 3 regions with shared electrons paired, and a region with a lone electron pair. These 4 regions are not arranged with a tetrahedral geometry because one region is a lone electron pair that fills a larger orbital. The lone electron pair